Hello, everyone. I was about to say good morning because it's morning in Paris. I'm Pascal Senella. I'm a CNRS researcher in the Center for Nanoscience and Nanotechnology, so close to Paris, here in Saclay. And I'm going to chair this second invited session of the day. We'll have 5 very nice invited talks covering a broad range of qubits from cold atoms, mechanical systems, NV centers, and photons. And the first invited speaker is Jing Zhang from Zhang University in China. And the title of his talk is One-Dimensional Superradiance Lattice in Ultracold Atoms. Professor Zhang, the screen is yours.
Okay, good afternoon, everyone. First, I would like to thank organizer for providing this opportunity to present our recent research work. I will give a talk about superradiance lattice in ultracold atoms. My group is in the State K Laboratory of Quantum Optics and Quantum Optics Devices at University. Outline of my talk is first to introduce the background. Superradiance lattice is an important phenomenon that relates to the quantum optics and topological physics. Then, present our recent experimental results of superradiance lattice in ultracold atoms. In quantum optics, superradiance is a phenomenon proposed by Dick in 1954 that occurs when a group of an emitter, such as emitted atoms, interact with a common light field. If the wavelength of the light is much greater than the separation of the emitters, then the emitters interact with the light in a collective and coherent fashion. The normal spontaneous emission is called luminescence, in which scattering rate is proportional to n. In contrast, scattering rate of superradiance is proportional to the n squared. Thus, the decay rate of superradiance became 1 over n gamma in here. In most works, each atom with 2 energy level is as a tiny dipole emitting light. Here, we employ the EIT energy configuration with the 3 energy levels. The excited state is coupled with another ground state by a pair of lattice lasers. Therefore, the excited...
Professor, sorry.
Yeah.
Tiny problem, there is a little sign in the middle of your slide that's hiding a little bit your slide. Can you remove that? It says StreamYard.
This one.
Yes, please.
Okay. Yeah. Put it here. Okay.
Thank you.
The excited state is coupled with another ground state by a pair lattice. Therefore, the excited state becomes the dressed state induced by optical lattice. In my talk, we also focus on the topological physics. Topology is a branch of mathematics that concerns quantities such as chain numbers that preserved under continuous deformations. In recent years, it has come to be understood that topology enters physics in very fundamental ways. Quantum degenerate gases offer us opportunities to efficiently simulate quantum condensed matter systems and study quantum optics and quantum information. Here, we focus on manipulating the kinetic term to generate a synthetic gauge field. We may study synthetic gauge field in the continuous trap potential, where manifold is a Cartesian plane. It means the momentum in dispersion curve is from the negative infinite to positive infinite. Recently, yes, our group mainly studies 1D and 2D spin-orbit coupled Fermi gas in the continuous trap potential. In parallel, optical lattice with synthetic gauge potential also has rich physics. The manifold is torus, describing the two-dimension Brilliant room. In this talk, I will focus on the new type of optical lattice system to generate synthetic gauge field and topological energy band. Here, I will give a quick show why our system can study topological physics. A pair of strong laser beam with same frequency forms a 1D optical lattice and drives the transition of two energy levels between excited and another ground state. Note here that one laser beam driving transition between the ground and the excited state corresponds to one photon Raman coupling. Thus, we can generate spin-orbit coupling and topological energy band with optical lattice. The simplest model that captures the main physics while at the same time providing good analytic insight is coupled boson or Fermi modes, which is inspired by the tight binding picture of solid physics. The corresponding Hamiltonian has the form of a collection of dependent boson modes in which tunneling between neighboring sites can be included as hopping terms. If the hopping term amplitude T is made complex number, boson mode behavior as they experience a synthetic vector potential. Here, I focus on the boson system. Usually, we do not direct diagonalize this Hamiltonian when it includes lots of boson modes due to very large matrix. We can transform the Hamiltonian into the momentum space with a smaller matrix to easily obtain the energy band structure. Feasible of realize this Hamiltonian is the BC in optical lattice with Boss-Hubbell tight binding model. Atoms are localized in the lowest energy band. Then we further generate topological energy band structure by manipulating with different coupling amplitude. Now we go to new system of 1D Superradiance lattice. A pair of strong laser beam with same frequency form a 1D optical lattice and drive the transition between ground and excited states. According to the Bloch theory, a pair of strong laser beam couples a series of the discrete momentum state with the integer 1 photon recoil momentum. Thus, the diagonal terms present the energy of discrete momentum states. Of diagonal terms shows the coupling between the discrete neighboring momentum state. When the intensity of a laser very strong, it means the coupling strength is larger than energy of a discrete momentum state. So we can neglect the diagonal terms. Then we can obtain the effective Hamiltonian with the discrete standard coupled boson mode. This system corresponds to the normal periodic structure of tiny binding lattice in momentum space. Now we look at the energy band structure of this Hamiltonian. There are two different spins, G and E, in the unit cell. We may obtain the effective Hamiltonian use the Bloch waveform and calculate energy band. The energy spectrum is composed of two bands, which are separated by a gap. The gap closed when only omega 1 is equal to omega 2. The two causing momentum, the Hamiltonian can be written the general form of Pauli operators in here, which corresponds to the SS model. The figure shows the locus of Hx, Hy as D run over the BZ of SH model. When omega is 1 is smaller than omega 2, the locus cover all the equator of the Bloch sphere as D run over the BZ, which means topological number is 1, and the energy band is topological. When the omega 1 is equal to omega 2, the gap is closed. When the omega 1 is larger than omega 2, the locus do not encircle the center of Bloch sphere or not cover all the equator of the Bloch sphere as D run over the Brillouin zone, which means topological number is 0 and the energy band is trivial. In order to detect energy band, EIT energy configuration and superradiance scattering are employed. The atoms are initially prepared in another ground state. The probe laser pump atoms into optical lattice coupled to energy levels. Then we achieve superradiance enhancement in certain direction of spontaneous emission and give the information of the energy band. Now, I briefly show our experimental setup of rubidium BEC. We employ the double mode structure, and the cold atoms are pushed from mode 1 into second high vacuum glass cell and recaptured in mode 2. Then cold atoms are loaded into optical plugged magnetic trap and perform RF evaporation cooling. At last, the atoms are transferred into the coarse optical dipole trap and further evaporation cooling to obtain the BEC. Here, the strong coupling laser is frequency locked by the saturated absorption spectroscopy to D1 line. The intensity of frequency of coupling laser are controlled by AOM. The probe laser is locked to the coupling laser by optic phase locked loop, so frequency of probe light can be adjusted precisely with large range. A pair of strong coupling laser beam of intersecting angle forms the optic lattice. The incident angle of probe laser must satisfy the phase matching condition in order to obtain superradiance enhanced directional scattering. Superradiance scattering is very weak in experiment, so we employ the EMCCD to detect it. In order to obtain the dark background and high signal noise ratio for detecting superradiant emission, the intersecting angle between the plane of two coupling beams and the plane of probe superradiant beams is set about 11 degrees. We measure remaining atom by the time of light absorption imaging after turning on the only one coupling and probe pass, rather than measure the transmit probe beam. The figure shows the EIT line shape with transparency window at the center. When we apply two coupled laser, we obtain a typical superradiance emission spectrum with two peaks are observed due to the density of state of 1D tidy binding lattice. The superradiance emission with standing wave coupled 3-level EIT configuration is different from the ordinary Bragg scattering. For example, a pair of strong coupling laser beam near 780 nanometer with far detuning from optic lattice, which generate atomic density modulation of ground state for the probe light. When scanning the frequency of probe light, we obtain the Bragg scattering spectrum. The spectrum is much wider and the width of the spectrum is not directly related to the Rabi frequency of coupling field. We study the superradiant emission spectrum as a function of detuning of intensity of coupling laser. With the coupled field detuning represents the gap opening and two dips corresponds to the one photon resonance of probe light. The separation between two peaks gets larger when increased coupling laser paths. The line shape of superradiance emission spectrum also depends on the incident angle of the probe light. In here, coupling laser and detuning. We also depend the angle of probe laser due to the phase match condition. The right peak can be turned low and left peak and change the angle of incident probe light. Due to the time limitation, I jump this work. I go to last work. Yeah, we also studied superradiance lattice by time correlated single photon counting technology. The short probe beam pulse are generated by high-speed integrate EOM with a 4 nanosecond duration and the 3.7 MHz repeated frequency. The scattering photon is detected by a single photon detector. The time resolved fluorescence measurement is obtained by time correlated single photon counting technology. This is a typical time resolved fluorescence decay curve of superradiance lattice. We can observe the quick decay rate with 5 nanoseconds, which is significantly faster than the natural line weights. Thus, we can demonstrate the superradiance characteristics of the superradiance lattice. We further study the time resolved fluorescence decay when changing frequency of coupling lattice beam as the crossover between the excited hyperfine splitting at the excited F equal 2. We find that the decay of EIT configuration has oscillation in the wing in here. The decay rate at the excited F equal 2 for coupling lattice beam is a little slower than the crossover between the excited hyperfine splitting. We further precisely tune the detuning of the coupling lattice beam in EIT configuration. We observe the oscillation frequency at the wing depend on the detuning coupling lattice. This phenomenon can be explained by the dressed picture. Inclusion, we generate a new type of superradiance lattice and use two technology to measure its features in frequency and time domain. Both results from two technology can be confirmed each other. In this system, we can further study photoassociation spectroscopy of weakly bound rubidium molecules near the threshold and manipulate the superradiance and the subradiance. At last, I would like to thank my group member. They work very hard on the experiment. At the same time, I would like to thank the happy cooperation in theory with Chad and David Zhang and Zhu Yao in Zhejiang University. Thank you for your attention. Okay.
Thank you so much for this beautiful talk and very impressive results. I will start the questions, waiting for the audience to contribute as well. The first one is about this the scheme that you're using to implement the SSH. If I understand correctly, for me, what I understand of the SSH scheme is that you have individual node and you have stronger link every other site, something like that, and then a weaker link. In your case, if I understand correctly, you have the omega 1 and omega 2 or between the excited state on one side and the next side. So I didn't fully understand how this maps completely to an SSH Hamiltonian. Can you just go back a tiny bit to that?
Okay.
I'm confused how using an internal degree of freedom for omega-1 and an external and a coupling degree of freedom of omega-2, it's equivalent to the SSH Hamiltonian.
You are right. So it's depends we select one parameter determine this omega-1, omega-2, which is a larger one. I know the mean is omega-1 and omega-2 is equal. Yeah, it means is 2. You can know this omega-1 equal to omega-2 is here is the gap is closed. Is have the degenerate point.
So are you showing inside right
yeah,
now?
when we change the omega-1, omega-2, larger or smaller one, we can change this this Hamiltonian encircle this center. This one is circle, this one not encircle this center. It means this is trivial. This is this is a topological band. Means the topological number is 1. For this case, is topological number is 0.
Yes. Yes, I understand. Oops. So I have another. I mean, I know the different platform for simulation based on atoms, but I'm not aware of this technique of using superradiance to implement a coupling. So first question is, what is the flexibility of these schemes? You've shown beautiful results on the SSH Hamiltonian. Can you have enough parameters to create more general Hamiltonian? Can you how many degree of freedoms can you play with to implement other Hamiltonians? And can you go to 2D crystals? And then how hard will it be?
Okay. Yes. How many parameters we can control, manipulate the parameter in our environment? Yeah.
Yes.
Yeah. We can control the lattice beam's intensity separately, such as omega-1, omega-2. This we change the intensity of the two lattice beam. Another way we also can change the detuning this lattice. So this we change the detuning. Here we detuning the 0. If we change the detuning, we can change this SH model, change it into the RM model, Rice model. So in our experiment, we can change all the parameters, like this detuning and this coupling strength. Yeah, we also can. This work I just not the talk. Yeah, we can add another lattice, generate the super lattice. So this generated super lattice, we can generate like synthesize the magnetic field.
Yeah.
Yeah.
And this is still 1D, right?
Sorry?
This is still 1D, one dimension.
Yeah, 1 dimension. Well, we also have the 2 dimension schemes.
Okay.
Yeah, in the future, we can do the 2 dimension or 3 dimension. We have some schemes.
Okay, thank you. Thank you so much. Again, I don't think we have other questions from the audience. So thank you, Professor Zhang.